Dear friends, welcome to Infos. Welcome to another video Infos. In this electrical engineering series, here also we are seeing the continuation of the last presentation, capacitors. Here we can see energy stored in a capacitor, charging and discharging current, how it is happening and the shapes. Then behavior of capacitor with AC as well as DC. So moving on. In the realm of electrical and electronics engineering, capacitors are key components praised for their ability to store energy in an electric field. One of the most crucial properties is its ability to block DC while allowing alternating current to pass through is used in the creation of high pass as well as low pass filters. We have seen in the last presentation how it can be used in the area of filtering. Then energy stored in a capacitor. When the voltage source is removed from the capacitor, that is in the second part of the figure, the second position of the switch, the two plates will retain its charge for a certain time. Thus, it acts as a source of electrical energy. Their ability to store charge is called capacitance, represented by C, and it is measured in farad. Farad is coulomb per volt, or C is equal to Q by V, and Q equal to CV, where Q is the charge and V is the voltage. We know I is equal to current is equal to dq by dt, where q is the charge. So current at any time instant t equal to c into dv by dt. Also, we have C is equal to epsilon A by D in terms of dimensions, where epsilon is the absolute permittivity of the dielectric material that is kept in between the two plates of the capacitor. That is in farad per meter permittivity. A is the area of one of the plates in square meters, and D is the distance between the plates in meters. So, we have C is equal to epsilon A by D. Then what is this absolute permittivity? Is a measure of a material's ability to permit electric flux. Energy stored, I am not including the derivations here, but the expression half CV square, when you substitute for CV, it becomes half QV. When you substitute for V, that becomes half Q square by C joules. That much of joules of energy is stored in a capacitor. Then we can see what is the charging and discharging current. In the last presentation, we have seen what is the charging and discharging voltages. Here are the currents. During charging, the current starting at its maximum value and decreasing exponentially over time, approaching zero. There is no voltage across the plates in the starting. Only source voltage is there and the start. That is why the starting current is maximum. As per Ohm's law, I is equal to V by the resistance. Then V, there is only source resistance. As charging started, then what will happen? We can see. As the capacitor charges, the voltage across it builds up, which opposes the source voltage and reduces the effective voltage driving current. That is why the current goes on decreasing. So this causes the current to decrease until the capacitor is fully charged to the source voltage and the current becomes zero, as I is equal to net voltage by resistance. Here Vs minus the voltage developed across the capacitor, then Vs minus that much voltage becomes Vs minus that much voltage, they are equal. So the numerator becomes zero, so the current becomes 0. So finally, as time goes on, the charge reduces to 0. That is why the charging of capacitor, the graph is taking that shape that is shown in the upper part. Then the charging current, the expression, mathematical expression. During charging, we have seen the charging voltage Vt equal to V0 into 1 minus e raised to minus t by Rc. Likewise here for Qt equal to Q0 into 1 minus e raised to minus t by Rc. Here also current is the dq by dt. That is why the expression for current It equal to I0 into e raised to minus t by RC, where I0 is equal to RC, Q0 by RC. T equal to 0, I of t equal to I0, that is the maximum current. That is why the shape of the charging current was like so. During charging, electrons flow from the negative terminal of the source to the capacitor's negative plate and from the positive plate back to the positive terminal. That is shown in figure. You have to see and understand thoroughly during charging how the flow of current or the electrons, then what will happen while discharging. How is the flow of direction of conventional current? During discharging, electrons flow from the negative plate through the external circuit and back to the positive plate to equalize the charge. That also you can see when in the discharging mode, from negative plate to the current is flowing and coming back to the positive plate. That is shown here. Then the shape of discharging current and charging. And the upper part shows the charging current while the lower part shows discharging current. That is the graph shown. The discharging current graph also starts from the maximum value, same maximum value. It is due to the fact that now the capacitor is fully charged. As the charge leaves the plate, the current decreases exponentially until it reaches zero when the capacitor is fully discharged. The discharging current is in the reverse direction of the charging current because of reversal of charge flow that we have seen in the last slide. How in that figure you have seen what is the direction of flow during charging and discharging. So that is why the shape of the charging current in the upper part and shape of the discharging current in the lower part. So if the maximum value in the upper part is say 5 millivolt, then in the lower part it is minus 5 millivolt. Mathematically, what is the discharging current? In the graph, charging and discharging voltage that we have seen in the last slide presentation, that is shown the upper part. Here the current, the charging and discharging currents. During discharging, the stored energy is released, causing electrons to flow from the negative plate to the positive plate through the circuit, which is the reverse direction of the initial charging current. And mathematically, Qt equal to, as we have seen in the case of voltage, here the charge Qt equal to Q0 into e raised to minus minus t by RC during discharging. Then the current, that is dq by dt, how it is minus I0 e raised to minus t by RC. Okay, when t equal to 0, it equal to minus I0, that is the maximum current in magnitude. Magnitude is same, the direction is negative, opposite, where I0 equal to Q0 by RC. Then how is the behavior of capacitor to AC as well as DC, that we can see. Actually, capacitors pass AC and blocks DC. How? In a DC circuit, the capacitor is initially allows current to flow until it gets fully charged with source voltage. The dielectric material between the plates is an insulator, so no DC current can pass through the physical gap. That is, it acts as an open circuit for a DC. In an AC circuit, the capacitor continuously charges and discharges as the voltage polarity alternates, and that enables AC current to pass through the circuit. It is an important property and it is also interesting. The capacitor opposes this flow without dissipating energy as heat. Another particular behavior of capacitor. This opposition is called the capacitive reactance, represented by X of Cx is equal to 1 by 2 pi Fc, where F is the frequency of the supply voltage and C is the capacitance value. We have seen it blocks DC and allows the flow of AC. Then it is quite interesting. Then why we are studying with DC? In the first figure also I have shown a DC source, a battery. Then why we are keeping DC source for studying? Studying a capacitor's behavior with DC voltage is fundamental because it establishes a baseline for understanding its reaction to an unchanging static voltage source. Then we can see, then it is easy to understand what is the behavior of or what is the action of capacitor in AC. That is why. This processor teaches how a capacitor charges to block DC by acting as an open circuit, which is a key concept of its use in both AC and DC circuits. So we have already seen in the last presentation, these capacitors can be used as a filter. Here we can see by the property of this Xc capacitive inductance, it can be used as a low pass as well as high pass filter. From the name itself, what is meant by these two terms, we can understand. Okay. The working of capacitor as filter mainly depends on the capacitive reactance principle. The capacitor, a reactive device, offers high resistance to low frequency signals and low resistance to high frequency signals using the formula X is equal to capacitive reactance. X is equal to 1 by 2 pi Fc. That means X is inversely proportional to frequency. That is, a capacitor gives dissimilar impedance value for dissimilar frequency signals, but a resistor is not so. That offers same resistance to a 1 Hz as well as 100 kHz signals. So a capacitor can be works as a high pass or low pass filter that allows high frequencies or low frequencies to pass respectively. So we have seen capacitor, how it is behaving to AC as well as DC, then the charging and discharging currents, etc. And also the energy stored in a capacitor. An important property. Capacitors are essential passive components in industrial electrical systems with the primary function of managing voltage. The key characteristic that distinguishes capacitor from batteries is that capacitors can release the stored energy very quickly to meet the sudden demand of power. It enables vital industrial functions including filtering, power conditioning, motor control, and power factor correction, which ensures system efficiency, reliability, and cost effectiveness. Thanks for the patient listening. Please join our Telegram channel and good day.